Right, so we said we're going to look at Arenediazonium ions and their reactions. And then later on we'll look at the NAS reactions. So we said that you can, if you take benzene, you can convert benzene first with the nitrating mixture, which is concentric acid, nitric acid. You will make nitrobenzene. You can then reduce nitrobenzene with tin and HCl, right, followed by base, and that's going to give rise to the aniline. The aniline can then be diazotized using sodium nitrite with HCl at 0 to 5 degrees Celsius. And that gives rise to the benzene diazonium ion. The benzene diazonium ion itself is a very reactive species and undergoes a wealth of chemistry. I'm going to use the second page. It undergoes a wealth of chemistry. So I'm just going to write it like this. And it undergoes reactions including the following. So there's a series of reactions called Sandmeyer reactions, where it reacts with CuX. X will be equal to chlorine, bromine, or Cn. This is copper 1. These are called Sandmeyer. Oh no, this is Sandmeyer reactions. And what you get is the corresponding substituted product. So you can get chlorobenzene, bromobenzene, or cyanobenzene, right? By replacing, it's a replacement reaction, replacing the N2 plus by the species. If I wanted to replace, if I wanted to get a fluorine on, it doesn't work well with a Sandmeyer, but it does work well with fluoroboric acid. Right, so HBF4 with the diazonium ion will give rise to the fluorobenzene. Regular old potassium iodide will give rise to the iodobenzene. I could actually get a phenol on if I allow this to warm with water. So I put on a hydroxy group and I make the phenol. If I treat this with orthophosphorus acid, so you remember H3PO4 is phosphoric acid, H3PO3 is phosphorus acid, so H3PO2 is hypophosphorus acid. So if I treat this with hypophosphorus acid, it puts on a proton, right? It puts on an H instead. This reaction is actually pretty useful from two perspectives. It gives me a way to put on a D onto the benzene ring, right? I can use D3PO2. Or you can actually use it as a way to use the amino group for its powerful directing ability and then get rid of it. So there's a classic example, which is how would I convert benzene into 1,3,5 tribromobenzene, right? And this is a problem, of course, because when you put the bromine on, the bromine tends to deactivate the ring. So the way you do this is you take the benzene and you convert it. This will take a couple of steps. One is you can use again the conc nitric acid, conc sulfuric acid, which gives you the nitrobenzene. 2, tin and HCl, right? And then 3, hydroxide, that gives you the aniline. And then 4, Yeah. So once you're at the aniline, what you would do, which gets you here, is you will treat the aniline with bromine water. So if I use bromine water, we talked about this a couple of days ago, this will undergo immediate reaction to give rise to a white precipitate, which is the tribromo species. So my diagram is not working very well here, but this we are bromine the para position. And then what you do is you diazotize. So you use basically nitrous acid, cold, right? That's a cold sodium nitrite and HCl. And then you use hypophosphorus acid, and you convert your NH2, or eventually diazonium ion, into the H, right? And you get that product. So diazonium ions undergo a range of reactions which are simply substitutive. But they can also undergo another set of reactions. So these are just substitution reactions. These are substitution reactions, right, of diazonium ions. The other reaction that they undergo, if you look at the structure of a diazonium ion, you can tell immediately that this is prone for a nucleophile to attack this species. The pi bond will break, and what you'll end up with is a species that looks like this, right? And this is called a diazo compound. The nucleophiles vary a great deal. The only ones we're interested in for this course is an activated aromatic. In other words, a benzene ring with either a phenol or an aniline, either an OH group, which is a phenol, or an amino group, which is an aniline attached to it. So for example, if I take my diazonium ion and I treat it with a phenol, so you know that the OH group is electron releasing. So now it'll attack the diazonium ion, and what we get is this species. Okay, this intermediate, then some base will come in, pull off the proton, and what we get is our final product. This product is interesting because obviously in this step this is a re-aromatization, right? What we get here is a species that is beautifully conjugated. And as a result, these compounds tend to be colored. They absorb light in the visible band because their homolumo gaps are now very short because of the extended conjugation. So instead of absorbing light in the ultraviolet band, they absorb light in the visible band, and so they appear colored. As a result, they're often used as dyes, and so they're called azo dyes because of their azo group. Turns out this is a wonderful science, and it was back in the 50s and 60s because that's how people used to color clothes. They would color food, right? This was food coloring. And what you would do is to solubilize it, for example, is you would put on, you know, SO3 groups, SO3H groups, and so on, or carbonyl groups or whatever, that would do two things. By putting on groups that are hydrogen bonding, SO3H, carbonyls, other OHs, and so on, you solubilize the compound, which made it able to get onto the fabric pretty easily. But also, you can change the color, because if you extended the conjugation appropriately, with a para substituent here, or an ortho, or even a meta, you could modify the frequency at which the substance would absorb light. And so you could change the color. And there's a well-defined science as to which groups to put on where to get a particular color, to get a particular property. It turns out a lot of these azo compounds are actually toxic, and so this area of the science actually sort of disappeared as the toxicity became obvious. I will point out, I've drawn this as if the para position only attacks, That is not the case at all. I can certainly get attack from the ortho position as well. I can certainly get attack from the ortho position as well, right? And so I could have, I can go bang, bang, and do the requisite chemistry. Sometimes it's appropriate, for example, if I wanted to get only attack at the power position, well, what I would do is I would block the ortho positions, put a methyl here and a methyl here. So the orthos were used up, and therefore the reaction will be forced to go at the power position. Okay, so the last thing we look at, so those are reactions of Arenediazonium ions. One is just substitutions, and the other is formation of azo dyes. So formation of azo dyes. The last thing we look at is a little bit interesting, well, it's actually quite interesting, which is called nucleophilic aromatic substitution. So these are NAS reactions. I remember when I was an undergrad and we were starting NAS, I had great difficulty grasping the concept because we had learned that benzene, by virtue of the pi electrons, was a nucleophile. And nucleophiles don't react with nucleophiles. And so, I remember for the first lecture, my mind was just completely racing that this was just impossible stuff. Turns out it's not. So these reactions occur in two different ways. So let's start off, let's say one via benzene. Yes, that's an odd looking word. Yeah, via benzene. So it turns out if I take chlorobenzene and I heat it with molten, this is not aqueous, this is molten sodium hydroxide, I make phenol. Right? This is called the Dow process. Right? And you guys know of Dow chemicals. This is one of the reactions that made Dow literally into a major player on the industrial chemistry scene. Because phenols are used in a range of purposes. Well, it turns out that this reaction, if you study it, because when you ask the question, no. Right. I'm assuming you guys can still hear me? Yes, good. So, if you try to study this reaction mechanistically, you have to ask, well, how does the reaction go? Well, it can't be, clearly the nucleophile is hydroxide. But this is not a reaction of RCl with hydroxide, right? In other words, that can go in a nice SN2 reaction, and I can get the corresponding alcohol. That's not how this reaction goes, right? It can't be. Because, this requires a backside attack. This thing is planar, so that would require the hydroxide to attack from here somewhere, or maybe dive in to the pi electrons, which is going to be very difficult because those are all electron rich. So this is very odd as to how this reaction occurs. So what is the mechanism for the reaction? Well, it turns out one of the better ways of studying it is the following. Most people believe that the way the reaction occurs is that the halogen, as you might expect, makes this H somewhat acidic. Now, this is not terribly surprising. We've seen in E reactions that hydroxide can do this kind of reaction. And if this H is 1, 2, 3 bonds from the chlorine, this is 1, 2, 3 bonds from the chlorine, surely if I can do this, then maybe I can do this as well. So the idea was that maybe the hydroxide is going to attack. When it does, if I deprotonate, that will generate water, and it will generate a carbanion, an aryl anion. That can then kick out chloride and generate this species. Now, I'm going to draw it two ways. I'm going to draw it like this first, And then I'm going to draw it like this. So this looks as if it's a triple bond. So don't freak out. It's not what you would consider a triple bond. It's actually 3 bonds between 2 atoms, but it's not a triple bond. And let me explain the little subtle difference between those two ideas. In a normal triple bond, my p orbitals, because they're sp hybridized, right? My p orbitals overlap. This is coming out to the board, and going back in. My p orbitals overlap here, here, in the front of the board, in the back of the board. And then the front, the top and the front overlap, the front and the bottom overlap, the bottom and the back overlap, the back and the top overlap. And they do it again. Here, 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 here. So what you actually get is a cylinder of electron density around the carbon. Right? You get a cylinder of pi electron density. So all of these things, there's this overlap of all of the p orbitals. In the benzene, if I were to draw my benzene molecule like so, I've got my p orbitals, my p orbitals, my p orbitals, my p orbitals. These overlap top and bottom, right? So we make my aromatic nucleus. But now what happens in benzene is that these 2 carbons, what you end up with is a bond. You get orbitals this way. These overlap this way, but not topwise. So they don't overlap here or here. And the reason we don't is because we want to protect the aromatic nucleus. So we dare not mess with these electrons, right? We don't mess with these electrons in the system, because if we did, we'd end up with 2 more electrons in the pi system. We would have lost aromaticity. So although we have 3 bonds, it's not a triple bond, right? So when we draw benzene like this, it's not a bent triple bond, okay? Which is why many people prefer to draw benzene in this fashion. So this species is called benzene, right? It's kind of benzene, and you kind of see 3 bonds, so you kind of think of a triple bond. Some of the best evidence for the formation of benzene is the following. If you take chlorobenzene and you make it with a carbon that is radiolabeled, so let's say the ipso carbon, the one that actually has a substituent, is maybe carbon 14. When you treat this with hydroxide, molten, what you actually end up getting is this compound and this compound. One with the label and one with the label there. So what this tells me immediately is that, as we said earlier, the mechanism is not just a simple SN2, because if it were, the hydroxide would replace the carbon bearing the chlorine and end up only on the ipso carbon. In other words, the only product you would gotten is this one. The fact that we're getting another product, in other words, we're doing chemistry in adjacent carbons, that suggests that there's some sort of a pi bond between the 2 atoms. And that is one of the biggest reasons why we end up with a benzene as our intermediate. So the way the reaction occurs, again, is that the hydroxide pulls off the proton. We generate our aryl anion. Right? I'm going to keep my ipso carbon. That is attacked. That is kicked out because I lose chloride. Good leaving group. That generates my benzene. Now the benzene is an electrophile. Right? It's electron poor and it's particularly strained. So it can now be attacked by the hydroxide, but the hydroxide can either attack, these 2 carbons are equivalent. If the hydroxide attacks here, right, then what I'll get will be this species, OH, with a minus charge. And then eventually, when I add water at the end, that simply picks up the proton and gives rise to my product. Obviously, the hydroxide could have attacked this carbon, in which case the minus charge ends up here, and the OH there. So when I pick up water, what I'll end up with is the H on the carbon with the asterisk, the carbon-14, and the OH on the carbon adjacent to it. So this mechanism, this mechanistic study actually proved or supported the existence of a benzenic or benzyne intermediate. So how do we know we get benzyne? Under what conditions do we get benzyne? Well, we need to have a good leaving group. There was a chloride, because the chloride has to come off. And our conditions must be very forcing. This is molten sodium hydroxide. This is not aqueous sodium hydroxide. This is molten sodium hydroxide. These are very forcing conditions. Turns out there's another way that we can do nucleophilic aromatic substitution. And again, by the way, I didn't say it plainly, but that's what we did. We had a nucleophile, OH minus, substitute on the aromatic ring. So this is nucleophilic aromatic substitution, NAS. But this one goes via benzyne. There is another type of nucleophilic aromatic substitution which occurs via the Meisen-Heimer complex. Right? Via the Meisen-Heimer complex. And the way that reaction occurs is a little bit different. So let's start off again. I'm going to have a good leaving group, chlorine. But this time, I'm going to have a really strong electron withdrawing group, typically nitro, but cyano can work as well, but it's typically nitro, located on the ortho or para position relative to the leaving group. So I need a good leaving group, chlorine, bromine, iodine, and I need a strong electron withdrawing group, one that does it by resonance, ortho or para to the leaving group. When I treat this with, let's say, hydroxide, aqueous, notice it's not molten this time, even if I were to put a label on this carbon, what I get as my product is this species. So I don't get the companion thing as I did with the benzyne. So clearly, this mechanism, right, because you see I got the group coming in at two different positions, right? Clearly, this mechanism is not via the benzyne, right? So the OH ends up at the ipso position. So how does this reaction occur? Now, first of all, let's identify the differences. The differences are, I have, yes, the same good leaving group, but I have a nitro group, ortho or para to my leaving group. My conditions are not as forcing. So I could use aqueous hydroxide, I could use cyanide, right? If I could use cyanide in DMSO or something, right? And I would end up with this compound. So I'm not using any strong base in this reaction of necessity, right? The reaction occurs with any decent nucleophile under appropriate conditions. So how does this reaction go? Well, what happens is the nucleophile actually, let's say it's cyanide, attacks the ipso carbon, which then dumps electron density, the influx of electron density, onto the waiting nitro group. And what you end up with is a negative charge spread over the nitro group and two groups on your ipso carbon, or it was once the ipso carbon. This is called a Meisen-Heimer complex. The Meisen-Heimer complex is unstable and spits out the leaving group as it re-aromatizes, and you generate your product. Right? So overall what you've done is a replacement of the chloride by the cyano group, right? So I'm going to lose chloride to give the corresponding product. And it's a direct replacement in the sense that you're replacing the Cl from where it stands. It's unlike the benzyne. Obviously, the reaction becomes more facile if you have more than one nitro group appropriately replaced. So if I have Cl and I have a nitro group on the ortho and the para position, this reaction goes much more easily. Lower temperature, shorter reaction time, and so on and so on and so on. So what you need is, and you can tell the difference between the reaction via the Meisenheimer and the benzyne, because in a Meisenheimer, yes, I have a good leaving group, but I must have a nitro or a cyano, ortho or para to the leaving group, and my conditions are not forcing. I'm not just using hydroxide, molten hydroxide. I'm using aqueous cyanide. I'm using cyanide and DMSO. I'm using iodide in acetone and stuff of that nature. To do the benzyne, I have just the naked leaving group, right, unstabilized in any way, right, and I'm using very forcing conditions, so molten sodium hydroxide. I would make a little point that in the reaction via the Meisenheimer, it's intriguing to note that there is a companion intermediate, which is the Wheeland intermediate, or the Arenenium ion, when electrophiles attack the benzene ring. This is your Wheeland intermediate, or it's called your Arenenium ion. This is intermediate for EAS reactions. This looks very different from the intermediate formed during nucleophilic aromatic reactions. Right? This is your Meisenheimer. This is for NAS. This is your Meisenheimer complex, which you form during this particular type of NAS reactions. Obviously, another intermediate you form during NAS reactions is benzyne. Okay, so this is the benzyne as an intermediate. Okay, at that point we are done, and great. I'll see you guys later. Bye-bye.